Okay, so we are all clear, is that right? For low pressure ammonia synthesis, we need a normal separation. We should not use the condensation high pressure separation. Okay, so first, let's talk about it. Okay, so this is basically the process simulation, process model, different cases. I'm going to go through the one by one, and then so essentially for simplicity, the Haber-Bosch the process, we basically break into three sections. One is the feedstock, the recycle and compression. Remember the feedstock, the recycle compression. That's one very important because the ammonia synthesis is not 100% conversion. The single pass conversion is not 100%. That means you need to recycle. So then we have the reaction part, and then there's the downstream separation. Okay, so the base case is the Haber-Bosch case. Okay, so this is the base case, and then we use the cryogenic case. Okay, case number one. So for the techno-economic analysis, all these new cases are the low pressure cases, and then they are comparing with the base case. So I want to make sure everyone's clear. All right. So you build the base case, and also you have the different cases. So case one is the high pressure multi-stage microwave reactor. So it is a microwave driven reaction, operate at 35 bar, and then not 275 bar. And then the downstream separation is a cryogenic flash separation. So I'm going to talk about what is the cryogenic flash separation. Okay, I'm going to break this one by one. Okay, case two is the high pressure, the multi-stage microwave reaction. Even if it's high pressure, it's only the 35 bar. So then let me see this case two. So case two, we have the interstage, the membrane separation. I'm going to talk about the ammonia membrane. Okay, so you can tell each stage they are different. Okay, now separation different. Here we use the cryogenic separation, which is similar to the Haber-Bosch. Here we change it, but reactor is always a microwave. So today, all this the reactor, low pressure operation, they are microwave reactor. Okay, and then I'm using membrane and the cryogenic the flash separation because this combined the membrane separation. Case three is the high pressure multi-stage microwave with a vacuum temperature swing at absorption. So the keyword here is the vacuum temperature swing at absorption. So that's so many cases. I don't think you need, I don't want you to remember that, but I'm going to show you one by one. Okay. So you understand there are a lot of the technology you can utilize when you reduce the reactor pressure. Case number four is the microwave, and then it's the pressure temperature swing operation. There are two different types of the swing operation. One is the vacuum, the other under pressure. Okay, so let me see if I have anything else. All right, so basically, look at this highlight. Case one, case two, case three, case four. The downstream separation, they are all different from Haber-Bosch base case. And also that's number one. Number two, the differences is the reactor pressure. Haber-Bosch reactor, we chose 282 bar, and then other reactors are 35 bar. Okay, make sense?
Yes. Yes, sir.
And case four, we break down in 4A, 4B. That's the detail. So first, I want to show you how the technology on the different separation. Then at the end, I'm going to show you the whole TEA. So it's going to be this section and another section. Today is a 3-hour session. We just finished 1 hour. So this is the second hour. We are going to talk about the different separation technology, so you understand why you want to do the low pressure the separation. And then we are going to show you the TA. Okay. All right. So I want you to spend 1 minute to read it. It's called the vacuum temperature swing adsorption. If you, I'm not sure if the audience has the, is familiar with this vacuum temperature swing operation. It's called the VTSA. If anybody I've heard of it, I don't have to interpret it to you, but I want to make sure you understand the process. Can someone say something?
Yes. We don't come across like.
Yes or no? Do you know vacuum?
No,
do you know VTSA? Or yes or no? I cannot hear it.
No, sir.
Okay, no, okay, that's good. I need to spend some time. Yeah, as I mentioned, the microphone you have in the classroom, it has some kind of feedback that I cannot hear clearly. That's why I always ask you yes or no. So yeah, so I can hear. So no, answer is no. I'm going to interpret it. So keep in mind, in downstream separation, what you need to separate: ammonia, hydrogen, and nitrogen. All right. So after the Haber-Bosch reactor, so let me put it this way. If you look at after the Haber-Bosch reactor, that's 3 components. All right. Ammonia, hydrogen, nitrogen. Ammonia need to separate it. Hydrogen, nitrogen need to be recycled. Okay. So this is 3 components we need to separate. So that means we need to condense or make the ammonia coming out. So the VTSA refers to a process where it's a solid solvent. Keep in mind, it's solid solvent. Okay, and then the material is used to capture a specific gas. Here is ammonia from a mixture by alternating between adsorption at ambient pressure and temperature, and the desorption at a significantly lower pressure and elevated temperature, and effectively swing between the 2 states to release the captured gas. Let's see in adsorption scenario. Okay, in the adsorption the scenario is under the pressure and the temperature. So once ammonia adsorbed, the hydrogen, nitrogen basically release. All right. So then you need to ammonia is adsorbed on a solid solvent. You need to let the ammonia go before then you regenerate the solvent. So you do the next adsorption. All right. So that's why the desorption is under vacuum. The reason you're under vacuum is because you want the ammonia come out. All right. So there are 2 operation mode. One is adsorption, the other is desorption. Adsorption means you adsorb the material under pressure, and then you release it, and then under the vacuum and elevate temperature. So temperature and vacuum will push ammonia out, and then you can refresh or regenerate it. So I'm going to stop here. I'm asking questions. So in the adsorption process, okay, here's a question. Is adsorption endothermic or exothermic? I'm gonna post the question.
Endothermic, sir. Endothermic, sir.
So adsorption is endothermic.
Yes, sir.
So that means endothermic need heat.
Yes, sir.
Are you sure? Okay, so is endothermic, is adsorption endothermic or exothermic? You said answer. All right,
Yes.
that's your answer.
Yes, sir.
Is your answer, is that right? Endothermic.
Yes,
Okay. Next question. Okay, here's another question. Is desorption? No, my spelling is wrong. Okay,
Other way around, sir.
is desorption endothermic or exothermic?
Endothermic, sir. Actually, we have changed. It's other way around, sir. The answer is endothermic. Absorption is exothermic, endothermic, and sorry, exothermic.
You change your answer, is that right?
Yes, sir. Yes,
So,
yes.
so basically the answer is
Yes.
makes sense, all right? Yep. So if I don't ask you the second question, you still say the first reaction isothermic. So these two process has to be opposite, right? One endothermic, the other has to be isothermic. So now you first answer, you say it's endothermic. When you ask question, you realize, oh, it's a desorption endothermic. Yeah, of course. When you read this desorption, why desorption is endothermic? Because you need heat and then to the release molecule. So that basically reminds you, oh my God, the adsorption is isothermic. Okay, so this is correct answer. So basically, the adsorption is different opposite of from the distillation or desorption. Distillation or desorption means you provide heat and then let the molecule go. All right. So that means if you adsorb molecule, that heat has to be released. Make sense?
Yes, yes.
Okay, cool. Okay, so this is the whole idea of this. Okay, now my next question. So you can keep on reading this. Okay.
Okay.
So you can keep on reading this. My next question is,
No.
does the pressure help adsorption?
No, sir. No.
Yes or no? That's all I need to hear.
Yes. Absorption.
Thank you. Yes. So answer is yes. The reason being that, it's gas solid reaction, all right? So when you have pressure, you force the molecule, which is ammonia, adsorb on the surface, all right? So that's why the opposite the process is a vacuum. It's if you want to dissolve the molecule, you need a vacuum, all right? So you apply pressure, adsorb, and you put vacuum, let release. So if you see the word elevated temperature, that means you increase temperature. Increase temperature means you basically speed up endothermic reaction. You follow me? So, and then put a vacuum and then help the molecule to release. So basically adsorption in this case is under the pressure and then certain temperature. When you go to dissolution, you need to pull vacuum and also the what you call that and increase the temperature. Make sense? This is the whole idea of vacuum temperature swing at absorption. Any questions? Is it clear?
Yes, sir.
Sir, it's clear, sir. But after telling this, I have one doubt. What is the difference between the pressure swing absorption and the temperature swing absorption?
Go to next. It's all the pressure. So it's all go by the so-called you are talking about PSA. It's all go by the delta P. So here the delta P is basically it's a vacuum and ambient pressure. See the keywords here. It's ambient pressure. So PSA means you absorb under pressure and then all of a sudden you release pressure. So that delta P is important. It's a delta pressure, not absolute pressure. You follow me? So here you absorb at the ambient pressure. That means the molecule is forced to the surface under the ambient 1 bar, and then all of a sudden you put a vacuum, you release it. PSA is the same thing. You apply maybe 10 bar, and then all of a sudden you release a pressure. Is that delta P is important. So VTSA, PSA, the same theory. You follow me?
Yes, sir.
Okay. So yeah, thank you. Very good question. It's delta P very important in the pressure differences. So now, how does temperature affect at absorption? You answer my question already. Okay. So temperature is crucial parameter in absorption reactions. According to the absorption theory, absorption decrease with increase in temperature. You follow me? So that means if you want the ammonia adsorb on the surface, you need to decrease the temperature. Increased pressure doesn't help because if the solid solvent temperature is high, they try to push the ammonia out. So to say different way, according to absorption theory, you need to probably keep the solid solvent at a relatively lower temperature. Follow me? So ammonia can adsorb on the surface. All right. So increase temperature, dissolve. So just make sure you the temperature swing, there's a pressure swing. Okay. So adsorption is high pressure, low temperature help adsorption, and then the low pressure and then the high temperature help dissolution. It's yeah. So you have to play with the temperature pressure in the ammonia adsorption. So this is a very basic theory. Are we clear now based on this? Okay.
Yes, sir.
All right, let's go to next. Now I'm talking about, so in the adsorption process, you have a solid solvent. All right, solid solvent means you have some material has to adsorb the what do you call that ammonia, and then you have ammonia, and then you have a temperature and pressure. All right, so before I show you the answer, let's do there's the answer next. Okay, so just for the what's the factors affecting adsorption? Doesn't have to be ammonia. Can be carbon dioxide. Can be any gases. Okay. So in general, let's brainstorming. So what's the factors affecting the adsorption? I'm talking about adsorption, not desorption. Okay. So we already said, we already discussed. Right. Oh, jeez. Okay. So let's list the factor of pressure, all right? And then temperature. So temperature need to be low, all right? And then, yeah, I don't want to change my spelling. It takes me time. So as long as you can read my typing, should be fine. Pressure needs to be high. Okay. What else? Anything else?
The particle size of the molecule.
You say the particle or what? Molecule. Are you talking about the solid solvent, or you are talking about the molecule to be at the solve? Can you repeat your question? Can you repeat what you can you repeat again? I cannot hear you.
Particle size of the matter will be
Particle size of the solid solvent, all right?
yes.
Thank you. So basically, why particle size is important? Because it's the mass transfer, all right? All right, mass transfer means if you have big particles, you can only, because of for the material to adsorb on the surface, they have to adsorb, and then there's the mass transfer, the limitation here. But if you break the big particle in a smaller one, it's easy to access this material. It's basically it's really a mass transport, you know, right? Or mass transfer, or the, I would say, physical property effect, like a surface area, all right? The smaller the particle break, you break, the larger the surface area, the easy for the material to access. Very good. Okay, so particle size of solid solvent. What else?
Fluoride.
Say it again. Flow rate.
Fluoride.
Thank you. So flow rate is important because that's basically residence time. Flow rate means if you flow too fast, ammonia doesn't have a chance to interact with a solid solvent, all right? So then means that it will not absorb. So that's why when you design this the solid solvent, you know, there's a limitation on the flow rate. You can't flow very fast. If you flow very fast, nothing will adsorb. You're right. It's called in terms of chemical engineering, it's called residence time. Residence time means you have to either call residence time or you call contact time. So you have to give it enough time for the material, contact time between ammonia and solid solvent. Very good. Keep on going. There'll be more. So all you are talking about are the physical property, particle size, and also flow rate, pressure, temperature. Have you ever thought of those chemical effects? All right. Some solvent, they may be because ammonia is a polar material. Okay, so let me see. Let me show you. You understand what I'm saying? Polar molecule. All right. Essentially it's a base. It is base. All right. So chemical effect, any acidic nature. Okay. Any acidic nature of solid solvent will tend to adsorb more ammonia. All right, make sense?
Yes, sir. Yes.
Okay. All right. So we can keep on going for days. Okay. So because it's all related. I mean, you are talking about ammonia and then the solid solvent. But one thing we have to remember, so this called VTSA is not just adsorption, it's a dissolution. So adsorption basically this blue color helps how much ammonia you can adsorb. I mean, the more ammonia you adsorb, the better, all right? Because that basically help you. That shows how good your solid solvent, and then how the small your reactor, because for a given volume, you can absorb more ammonia. But don't forget, if you are absorb too tight, it's going to affect your desorption. You understand what I'm saying? So which means because this solvent has to be regenerated. You adsorb, you desorb. But if because adsorb is only half a story. You finish half cycle. That means you adsorb. If adsorb too strong, you cannot desorb. That's it. Your solid solvent is saturated. You cannot use it anymore. All right. So this has to be the swing. You see the keywords. Effective swing between the two states. So this is the key. So you have to design and or select a solvent that can effectively absorb ammonia, and in the meantime, effectively release captured ammonia. Make sense? Okay.
Yes,
All right. So yeah. If you understand what I'm saying, so I think we can keep on going. I don't want to just keep on, because there's just so many things you can list these days. So I have 3 top answer here. The absorption chemical composition, the solvent chemical composition, and the surface area. I think the number 1 is we already covered. Okay, so I really appreciate the student. So the particle size and the chemical nature. So that's covered here. Solvent chemical composition. I'm going to show you the solvent, okay, the chemical composition, and the surface area. Surface area is translated into the particle size, all right? So, okay, good. Second, the absorption gas physical characteristic temperature. So basically, this is gas, ammonia is base, okay? So then also what's the physical characteristic temperature? That means the gas has to be at lower the temperature, all right? Lower temperature, the more easy to adsorb. So this really tell you the temperature, gas, and the pressure. Remember, pressure helps force the molecule to adsorb on the surface. But this all talk about adsorption, but don't forget, you have the desorption. That's we are going to talk about that next. Okay. So, anybody has any questions?
no, sir.
So, let me talk. Let me show you a video, okay, YouTube video. You will see the pressure swing. I think some student asking about pressure swing adsorption. I'm going to show you the YouTube, and then we talk about the vacuum distillation. As I mentioned, it's all about the delta P, which means your adsorption, desorption has to be two different temperature, 2 different pressure. Otherwise, this material will not come out. So I'm going to show you a video, and then YouTube, and how the people doing what's it called, the so-called pressure swing operation. Okay. All right. So I'm going to stop sharing, and then when YouTube shows up, I will share with you. Okay. Okay. Let me see. I need to share. I need to share that Google with you. Can everyone see this?
Yes, sir. Yes, sir.
I'm pausing here. Can you see screen here that shows the YouTube on left hand side corner? Can you see it? Yes or no?
Yes.
Yes. Yes,
sir.
is that right?
Sound normally. No audience.
So this video is not about ammonia. It's about the pressure swing adsorption for air separation. Okay, the oxygen nitrogen. You understand what I'm saying? I
Yes,
paused
sir.
it.
Yes, sir. Yes, sir. For industrial use, we are using to separate oxygen and nitrogen for.
Yeah. So basically, after you watch this video, you understand same theory and same practice apply to ammonia. So happened I could not find the ammonia adsorption the YouTube. So now this is for it's the same thing. Okay, just keep on watching. It's only like I think 4 minutes long.
சொல்லுங்க சவுண்ட் வர மாட்டேங்குது இப்ப பாக்குறது இது மாறி மாறி ஆக்சிஜன் போகும் அங்க யூஸ் பண்றோமா அங்க பிசி அவங்க நீங்க யூஸ் பண்றீங்கன்னு சொல்லுங்க நான் அமோனியா தான் பண்ண போறேன் அடுத்தது உங்க லேப்ல வந்து பிசிஎம் புரோஜனம் இல்லை ஒன்றும் இல்ல அந்த இந்த ரியாக்டர்ல தான் நான் ஒர்க் பண்ணுவோம் சாப்பாடு அதெல்லாம் இல்ல நம்ம ஸ்ட்ரைட்டா அவங்க லேபுக்கு தான் வரோம் 2 வாரம் ஒர்க் ஷாப்லாம் அட்டன் பண்ணிருக்கேன்
மட்டும் பாஸ் ஆகும் இதை வச்சுதான் இங்க நைட்ரஜன் பண்ணிட்டு இருக்காங்க இல்ல ஆக்சிஜன் தெரியும் ஆக்சைடுக்கு வந்து தனியா இது வச்சு பண்ணுவாங்க கான்கிரீட் இதுல வச்சு பண்ணுவாங்க
நான் தான் எழுதி கொடுத்தேன் அதுக்கு உங்க லேப்ல ஹேபர் போக்ஸ் ப்ராசஸ் பண்ணலாமா இல்ல நீ லேப் பண்ணு அப்ப நான் நம்ம லேப்ல பண்ணேன்
Okay, I'm going to stop here. So everyone's clear about the pressure swing operation. The example they give here is for the air separation, but it's applied to ammonia as well. So you can think the ammonia will be separated from hydrogen and nitrogen doing the same way. All right. Any questions? What you learned from here?
No.
Anybody have any question? after
sir.
listening this PSA? No question?
No, sir.
Okay. All right, I'm going to stop sharing. And then let's talk about the rule of thumb of the separation, okay? So basically for any I would say the swings pressure swing at adsorption or separation. Okay, here's the deal. Okay. Okay, I'm gonna give a very good example. Based on the video, if you hear what they say, video is air O2. Okay, it's separated into O2 and N2. Okay.
Yes, sir.
So basically, you separate N2. Ideally, you want 100% pure N2 N2. Ideally, okay. So basically, pressure swing, you have N2 and O2, the mixture. So basically, I would say, I'm going to tell the rule of thumb. Okay, so how they set the. I think at the end, that video shows they obtain 95% of purity of the oxygen, and they are very happy because that's good for the hospital medical use. Whatever in the hospital for the emergency use, oxygen is not 100%, but that's not the case. The case I want to mention is the technical challenge. Okay, so you from the mixture of one N2 of this, which is air. You wish you have 100% N2, and then I'm talking about pressure swing 100% N2. Can you achieve that? That's my question.
Yes, sir. We can achieve, sir. Achieve. Absorption.
The answer is yes, but it takes a lot of
Energy.
the unit operation.
Yes.
Yeah, the answer is yes, but it takes a lot of. So what's the general practice? Okay. So what is the general practice? Here's the general practice. The general practice is more like this. You have to ask yourself, is oxygen important or nitrogen important? Okay. So you have to ask yourself. So if nitrogen is important for ammonia, okay. If nitrogen is important, so you basically push nitrogen to 100%. Okay.
Yes, sir.
100% N2. That means on the O2 side, you will have N2 left in O2. Make sense? To say different way, to say different way, O2 is not going to be
N2.
okay. I want you everyone read this. Okay, so this is so-called general practice. How you practice the pressure swing in the real world. Okay. Yeah, please read this, what I put in here. So what is general practice in PSA in the PSA? So if nitrogen is important for you, you push the process to achieve 100% nitrogen. That means on the nitrogen stream, if you look at that, it's 100%, but you have to sacrifice N2 and having them left over on the O2 side. That means on O2 side, you will have N2 left. To say different way, O2 is not going to be 100% pure. So it could be 90%, which is okay because your objective is N2. And vice versa. If you want O2 100%, that means on N2 side, you have oxygen left over. That's general practice and pressure swing. You will never get both 100%. It takes so many vessels, so many steps because you have to keep on purifying. It's not economical. Okay. So the economic way, general practice, you have to ask yourself, what is important? The important, then you do this. Follow me?
Okay.
The pressure swing. The other in general, that's why I want to share my real world experience with you. So I'm talking about a chemical refining operation, the separation called distillation column. Okay, this is distillation column. So what the distillation column does is it separate a component. Let's say you have component A and B. Okay, come into column. So on the top, so this is called distillation. All right. You have A, and then on the bottom, you have a B. Okay. So this is what you want. So if you look at any chemical plant or the refining, you have a mixture of A and B coming in. And then let's say the gasoline distillation. This is the gasoline, and then on the bottom, this is the heavy material, the B. Okay. So if you A is the most important to you, you want 100% A. So that means B has to have A left over here. That's the rule of thumb. Or you say no, I want B is pure. Your A has to have a B. Make sense? This is very general. Same thing, the distillation, adsorption, the separation thing. Any separation technology, you all, even membrane, we are going to talk about next. You are facing the same challenge. Is you have to ask yourself a good question. What do you want? Okay, so you want one stream A, that means the other stream will not be pure. Make sense?
Yes, sir.
Okay, let's keep on going. Yeah, please ask question because I'm going to talk about a lot of separation technology. So this separation, remember we talk about the property of the chemical effect. Acidic nature of the solid solvent will tend to absorb more ammonia. All right, just try to memorize this sentence. So when we talk about the importance of the solid solvent, we talk about chemical effect or the chemical property of a solid solvent to absorb ammonia. So now I'm going to tell you let's analyze the publication. So actually this publication is published in the American Chemical Society Applied Energy Material. And then the title is Optimizing Ammonia Separation very reactive adsorption for sustainable ammonia synthesis. What is reactive adsorption? Reactive adsorption means that a solid solvent is not just provide physical property to adsorb ammonia, okay? And it's not physical adsorption, it is actually chemical reaction. So the material they use is the magnesium chloride. Anybody can tell, if you read the structure, magnesium chloride is a little bit acidic, all right? Because let me put it this way, sodium chloride is neutral. Magnesium chloride, because the chlorine side is coming from HCl, is acidic. So intuitively, you will know the magnesium chloride will adsorb ammonia and then bond with ammonia. So that's why this adsorption is called reactive adsorption. It's not just adsorption, it's react. So the challenge here is, once react, how would you dissolve it? So when that means you have to decompose the complex. Make sense? So this is a publication in this. If you are interested, you can read this. And then I know this professor is from University of Minnesota. We use their data to do the simulation. In today's TEA, you will see we use their data, which is shown here, adsorption data, to basically to run out the simulation. So anybody has any questions?
No,
So if you look at the data, all we have been talking about adsorption theory works in here. I want you to take a look at if you see my cursor on the far right hand side, this is their adsorption data. It's so-called equilibrium capacity. Equilibrium capacity means they cannot, at equilibrium, they cannot adsorb ammonia anymore because it's reaching the equilibrium, the maximum they can do. If you look at the equilibrium ammonia adsorption on y-axis and versus the ammonium pressure, there are different color form. So first, increase the pressure, increase the adsorption. All right, we all know. So if you look at the increased pressure, all of this temperature increase. So different color coded line means adsorption at different temperature. It starts from 150 C, 200 C, 220 to 400 degrees C. Okay, so different color, different temperature, and then operate at a different pressure. At any temperature, so if you increase the pressure, the amount increase. Correct. All right. Pressure help adsorption. What about temperature? Did you see? It's the right line, 400 degrees C. It's the lowest equilibrium capacity. All right. Remember, adsorption is exothermic. Temperature doesn't help exothermic. So that means if you have a solvent at a higher temperature, the molecule ammonia doesn't like to adsorb surface. That's why low temperature you have higher absorption capacity. The moment that you increase temperature, it doesn't help the equilibrium capacity. Make sense? I want to hear the answer. Does everybody understand this curve on the right hand side? This is a very important curve. We actually obtain this data. We use this for our simulation. This is basically pressure temperature effect versus the equilibrium capacity. Anybody understand this curve on the right hand side?
yes, sir.
Okay, and also you also understand reactive adsorption. All right, it's not just simple adsorption. It's ammonia reacted with the magnesium chloride. Okay, all right. So this from this paper, and then let's go to next. So this figure caption is pretty long, and then I want you to probably read it maybe for 1 minute. Then I'm going to interpret this the curve. This is their experimental data, and then this is desorption data, and here is adsorption data. Okay, under pressure adsorption data. Now they start the desorption. Okay, so keep in mind desorption need the what do you call that? Need the temperature and pressure. Just read this. I will interpret to you. Okay. So basically, if, even at absorption and the desorption, there is the so-called the terminology adsorption kinetics. So that means how fast you can adsorb, all right? So some molecule interact with a solvent very fast. So they can just interact, but some are really slow. So adsorption kinetics. And then some is called desorption kinetics. And how fast you can push the molecule out of the surface. All right. So this is really the data. This the data very important. It takes time to obtain this data. So that means when you increase the temperature and also decrease the pressure, and then it takes time for molecule to leave the surface because this is reactive adsorption, and then ammonia is strongly bonded with the solvent. So it takes time, and it also takes temperature and takes the kinetic data. It's a lot of work. So all this has to be factored into your at the sober design. Sober means you downstream how big, how large is adsorber. So for sake of argument, if this is the material that takes 1 hour or 2 hours or 3 hours, much longer time to dissolve, that means your vessel has to be very big, allow you the time. All right. If dissolve is fast, that means your vessel can be small because you have a quick the turnover. But if the adsorb if this time lasts longer, you don't have, it takes a long time. So anyway, so all this time is dictate the adsorber design. Make sense? Anybody understand time effect? It's not just a temperature effect, it's not just pressure effect, and also kinetics, desorption kinetics. That means how fast the molecule can leave the surface. Anybody have any question here?
No,
No question?
no.
Okay. So let me. I think we in about 2 or 3 minutes. You guys need to take another break. 30-minute break. But before you take break, I want to show you. So all of the separation, we are talking about obtaining pure ammonia. So this is the objective. All right. So because you want the pure ammonia, this is the objective, because ammonia can be utilized for many industry sectors, like say the fertilizer, and then like the refrigerant, and also the today ammonia even can be combusted. So my question is, what if you just need ammonia to be used as a fertilizer? So I talked to a group of farmers in the United States. If you don't want to sell pure ammonia, you say, hey, I only sell ammonia, as a fertilizer. One separation technology is more like this. I want to make sure you understand. So basically, you have so what you need to put in here is solution. Oh. Okay. So what does it mean? But keep in mind, in this case, this is what I learned from the group of farmers. Okay. So in this case, you only want ammonia to be utilized as the fertilizer, not anything else. All right. So basically, ammonia, nitrogen, and hydrogen coming in, and then what happened with the ammonia when they see the sulfuric acid? Anybody can tell me?
It's nitric acid, sir.
What's the when ammonia see the
Ammonium nitrate.
okay? So that means ammonia will be in a solution, all right? So what ammonia is going to turn into? Ammonia will be turned into is that right? Make sense?
Yes, sir.
What is the ammonia sulfate? What is the ammonia nitrate? Are they fertilizer?
Yeah, ammonium nitrate is a fertilizer, sir.
Yes. So
Yeah.
ammonium sulfate also the fertilizer. But you
Yes.
all you need to be careful about ammonium nitrate. It's explosive, all right? So normally people, for safety, they actually turn into the ammonium sulfate. So this solution, if your objective is not to make the ammonia, pure ammonia, you can have a solution, and which is the sulfuric acid, and then you just put ammonia in there, then you end up with a solution of the fertilizer. Just sell that fertilizer to the farmers. It's much easier, it's cheaper. But for the general ammonia plant, nobody do this because it's only to make the farmers happy. But the ammonia has a lot of other use. That's why you need to do the pressure swing, membrane, cryogenic. Anyway, so I think it's about the taking break. So we will take a break and then come back in about 30 minutes from now. We are 2 minutes over. Let's take 30 minutes. Okay, right.
Thank you, sir.
All right. So see you in 30 minutes. Okay.
Yes, sir. We'll meet after 30 minutes, sir. Thank you for your
Yes.
session.
Yep. Yeah. See you.